highlight logarithm, and what a logarithm does is it is the inverse of a power. So if you took the graph of y equals 10 to the x, and if you think back to our transformations unit, we could graph the inverse by just switching all the x and y values and flipping it over a diagonal line. And you would get the graph of y equals log base 10 of x. So just like powers have a base of 10, their corresponding logarithm will also have a base. Now the base of 10 is a special one. It's the one that's on your calculator when you hit the log button, and it's called the common log. So here we have y equals log x being the inverse of y equals 10 to the x, and we've got a new function. So if you take points on your exponential graph, you just switch x and y, and those would be points on your log graph. But this is where, each thing has its own specialty as we get more complicated, like square rooting both sides, you had to remember plus or minus. Sine and cos inverse, you had the cast rule and reference angles. With logarithms, a lot of it is based on the definition of a logarithm and being able to switch something by its definition from its exponential form to its log form. So I would like you to write this down underneath the definition of the logarithm with those same letters. And what it allows you to do is anytime you want to solve for something, all you need to do is switch it to the log form, and it might help. And we notice in the log form that what's by itself in the log form is the x, which is the exponent in the exponential form. But there's still going to be some problems that we're going to run into. So for example, I had started off with how do you solve 7x equals 30? Well, according to the definition of a logarithm, you could rewrite this as log base 7 of 30 equals x. And if you can type that into your calculator, then you can solve it. But we're also going to find out that not all calculators let you type in any number here. Some do, some don't. So for example, I'll pull up my calculator, which does allow me to type in log 7 of 30, but some calculators don't. So we have to learn some additional rules for logarithms to help us figure that out. So for example, on my graphing calculator, if you have a newer version of the TI-84, either under the math button, which you have to go all the way down to the bottom until you get to log base, I could type in log base 7 of 30, and I get 1.747, which means if you type 7 to the exponent of this number, it should equal 30. And it does. The only reason it's a little bit off is rounding for decimal places. You might also find the log base under, right, if you go alpha F1, you get to the fractions. F2 gets you to some functions, and it's number 5 there. You could also get it that way as well. But some calculators don't have the log base button. They only have the regular log, which looks like this. And just interestingly, we're going to find out why this works later, that log 30 divided by log 7 happens to be the same thing. So, if you find that interesting, you could write that here. And when we write log without any base written, it's like there's an invisible base of 10 that's there, but not needed to be written. This definition is super important moving forward. So important that I'm going to give you 1 minute right now to see how you would remember changing from this form to this form. Where do things go? Which things go where? So if you have something in exponential form, could you change it to log form? And if you had something in log form, could you change it to exponential form? All right, let's go to example 1, and now see how well you memorize it. I'm going to give you guys a head start. For 1a, take each of those and write them as a logarithm. And then for b, take each logarithm and write it in exponential form. All right, let's see how you did. So, in log form, this would be log base 3 of 27 equals 3. Log base 5 of 1/25 equals -2. And log base 4 of 1 equals 0. And one of the things that I use for the definition of the logarithm is if the purpose of a logarithm is to solve for an exponent, then the exponent is always the answer. If the purpose of a logarithm is to solve for an exponent, something you haven't been able to solve before, when you use the definition, that's what's going to be by itself and solved for. If you know that, and you know that the base stays the base of the logarithm is the base of the exponential, then you basically got your definition memorized. Right, so same thing here. These are all what the logarithm solved for. So when I change those to exponential form, the base is the base, 2 is the exponent, 49 is the answer. 4 is the base, -3 is the exponent, 1/64 is the answer. 10 is the base, -4 is the exponent, 1/10,000 is the answer. And eventually, you're going to be evaluating logarithms. So you will get something like this, and you'll ask to be solved for it. And a visual that I find really helpful when evaluating logarithms. Okay, we already know that the answer to this is 2. But instead of writing it as exponential form, in my head, I say logs solve for exponents. So I imagine a little tiny question mark right there as an exponent. Can you see what 7 to what would be 49? Can you see that that would have to be 2? Right? On our powers chart. Log 3 of 81. This is asking what exponent would be there? Since log solve for an exponent. What exponent would be there so that 3 to that exponent is 81? On your powers chart, 3 to the 4 is 81. So I'd like you to circle questions 5, 6, and 8.